Hello again. We're actually still working on operation of functions, or operation on functions, but specifically we're going to talk about the inverse. And I remember this was a topic when I first did it. I never really understood what was going on, and it was always so difficult because if I didn't understand what I was doing, I just didn't want to do it. And then, eventually, like most of the concepts I've ever learned in math, you get them if you practice them enough. And before I continue with that, let me just state this little statement right here. If a function f and f of -1 are inverses, then f of a equals b if and only if f inverse of b equals a. Now that's a little hard to digest, but what I want to do is kind of show you something. And basically what you do is, if you can reflect a graph on the graph y equals x, if you can mirror it, that's an inverse function. So, like for instance, I'll draw a quick one right here. So I've got this right here. If it can mirror off this, then it's an inverse function. I don't know, like this will look like this. That's an inverse function. That's really what's going on here. All you're doing is you're replacing the y with the x's. That's what's happened graphically. That's actually a little bit easier to understand once you get the algebraic way of doing it. It's not too bad. So f of x equals x plus 6 over 2. I want to find the inverse. To make this a little bit easier for students who just want to do this, what I tell students is replace the f of x with y. And there's a reason why. Just do that for right now. So y equals x plus 6 over 2. If you want to find the inverse of a function, what you do is you replace the x with the y. That's it. So this will read x equals y plus 6 over 2. Pardon me. But this isn't actually the inverse, because what you have to do is you always have to solve for y when you want to graph, because you have an input and you have an output. When you do logarithmic functions, that's an example of that. So I'm going to replace the x with the y, but now what I got to do is I got to solve for y in order to figure out its actual inverse. So I'm going to go ahead and erase this and continue off this, because I'm going to need as much room as possible, I think, and go along with it. So if I want to get y by itself, let's figure out how to do that. And the first thing I'm going to do is I'm going to cross multiply, or I can just multiply 2 on both sides. But I just tell students to cross multiply because they buy into it more. So bam, you can't cross multiply anything with y plus 6 except for 1. So 2x equals y plus 6. Now y is almost by itself, I got to subtract 6 on both sides. And I get y, my voice, embarrassing, y equals 2x minus 6. That's the inverse of y equals x plus 6 over 2. But if you want the technical jargon now, what you're actually going to do is replace the y with the notation the inverse function. It's the same thing, but whatever. So that's the inverse of this one right here. It's a good way to catalog it. Now, that said, looking at this little corollary, this little problem right here, we're going to figure out what happens. And let me try to state it as best as possible. So let's use a value for x. Let's use 4. 4 is going to be nice. Let's use f of 4 here. So f of 4 equals 4 plus 6 over 2. F of 4 equals 10 divided by 2, which is 5. Now what this states is, well, if these two functions are inverses, then f of a equals b if and only if the inverse of b equals a. The inverse function of b equals a, pardon me. So let's look at this. A is 4, b is 5. Now I'm going to take the inverse function, which is this one right here, and I'm going to plug in the b value. Well, the b value was 5. So inverse of 5 equals 2x minus 6. Now what it's reading is the inverse of 5 should equal whatever the a value was. Well, the a value is 4. Let's find out. 2 times 5 is 10. 10 minus 6 equals 4. So that in fact does work. You know, if I substitute in 4 for my inverse function, I'm going to get a value. Well, that value, I'm sorry, if I put in a value into my function, it's going to give me a value. I take that value and I put it into the inverse, it's going to give me the input of the other one. Pretty cool. I think that's pretty cool, at least. It's very helpful when we start working with logarithmic functions. Square root functions are an example too, except you don't take the you don't take the negative aspect of the square root, and you don't take the domain below 0 on a quadratic, and then you actually have an inverse, you know, along the y-axis. It's cool. Yeah, so that's my last operation of functions, I would have to say. It's pretty cool. You use this, and will use this too, to start explaining functions like logarithmic functions. Square root functions are a little bit easier to understand, because you don't really need to understand that it's the inverse of a quadratic given from 0 to infinity for your domain of x's. But when you do logarithmic functions, it's essential to understand what's going on, because most people cannot do logs off the top of their head. Yeah, but we'll see when that ends up coming along. Okay, but for right now, have a great day.